Example 2 was interesting. Why was it interesting? Because something changed. All right. In example 1, pretty boring. Hal just sat still. But example 2, Hal moved. And that's what made it interesting. Actually, I'd go further. I would say it was fascinating. So since something changed, we need more variables. If we're going to get to the equation part of that example, we need a little bit more. So first, let's recall we know what x is. That's position. But for example 2, it changed with time. So we'll say AFO time. So you got to get used to some of my abbreviations. AFO means as a function of. Okay? I'll introduce you to T2 later, to equations 2 unknowns. But for now, we're just doing AFO. Right? So we knew that there was some x. We know it can change in time. We call it position. But now we need a new one. Okay? So the new one, we write delta x. We call this the displacement. The displacement, it equals the change in position, and here's the key difference, between two times. So a little bit of a difference. This one continuously changes in time. This is really two different times. So let's look at our equations. We're not going to quite get to the equation that describes the motion yet, because we need to really obsess with displacement for a minute. Let me give you an equation for displacement. It's equal to a final position minus an initial position. Like I just said, it's the change in two positions. Now in physics, you got to make sure you always get this right. It's always final minus initial. So I can give you an example. Say you go to Starbucks with $10 and you get a cup of coffee and you come out with $8. Right? What's the difference in your money? Just say it out loud. What's the difference in your money? Wrong. The difference in your money is negative $2. So I'm sure you said $2. Everybody says $2, but it's negative 2. It's final minus initial. It's $8 minus $10. So in physics, we got to keep up with these negative signs, and changes are always final minus initial. In language, we have words that mean the negative sign. I just blew $2, or I just lost $2. Or I just dropped 2 G's on some dubs for my Civic or something like that. So in that case, dropped means it's negative. But in physics, we have to get everything formally correct. Final minus initial, the numbers can be negative. Okay? Let's see. So we want to be sure we understand this. What do these mean? The position xf occurs at time t final. So if we were tracking the motion, we might have an initial time, and it's at one place at the initial time. We might have a final time, it's at one place at the final time. And you can imagine that the position x initial occurs at t initial. Two different times. These are positions, and that's displacement. Okay? Now, here's the tricky part. Here's where I'm going to deviate from most physics books. Most physics books start out with 1D kinematics, and that's all we're doing, one-dimensional kinematics. Only one way to go on the track. And therefore, they ignore vectors until they get to 2D kinematics. But I like to just bring in vectors right at the beginning. Well, let's just get it over with and talk about vectors. This is just life, right? Delta x is a vector. And that's why I put a vector symbol on top of it. Delta x is a vector. We have to deal with it, even in one dimension. So let's think, what does that really mean, that it's a vector in one dimension? What are we talking about here? And the way to think of it is we could imagine, let's go back to our x-axis, right? Here's the origin. And if I give you a delta x vector, a displacement vector, say equal to 3, what does that mean? That means I was at some position x initial, and I had some position x final, and the distance between them is 3. And the fact that it's positive means it's to the right. So that would be plus 3. If you get a negative value, then it would be the other way. Right? We could also have plus x. There's the origin. Doesn't actually matter where the origin is when you're talking about displacements, because they're just a change. But let's say delta x equals minus 2. That would be a case where you have an initial here and a final here, and the vector from initial to final points that way, -2. Okay? Now, one thing about vectors is you always have to have both sides be a vector, right? So you know a vector is a number with a direction, a scalar is just a number. So I said delta x is a vector. Clearly there has to be something to make 3 a vector, and it's called the unit vector, I hat. You put a little hat on it. And here, -2 I hat. I corresponds to the x-axis. Hat means it's a unit vector. It's just a little thing you put on there to say x-axis direction. And unit means its magnitude is 1. So you're multiplying these two things, but you're multiplying 1 times 3 is just 3. 1 times -2 is just -2. All it's really doing is identifying the direction. Okay? So right now, if you've never heard of that, that's freaking you out. You're panicking, screaming, turning off the computer. So don't worry about it. We'll do a lot more unit vectors. You'll get comfortable with it in time. But for now, to be formally correct, if I'm calling this a unit vector, I should probably say, okay, it's this difference, and put an I hat. I'll show you other ways to do the vector notation later, but for now, I want to put that on there. And we're going to think of these things as vectors.